Hi everyone, this lesson is going to look at percentage yield, and this carries straight on from where we got to with reacting masses. Now we are going to look at reacting masses again today as part of this lesson. We're going to go through a couple of examples of those. But if you know you found them a bit difficult before, it might be an idea to just go and look back over your notes to remind yourself of reacting masses before we carry on. If you are ready though, make sure you've got a pen and a piece of paper and definitely a calculator for today's lesson. I'd like you to get the date and title written down and then have a look at these starter questions. So we're going to think about the reaction between magnesium and oxygen to form magnesium oxide. And number one, I'd like you to write the balanced equation for the reaction. And then number two, have a go at this reacting mass calculation. If we started with 0.1 grams of magnesium, how much magnesium oxide would we expect to form? So pause the video, make sure you've got the date, title and have a go at those questions, and then press play when you're ready to hear the answers. Okay, so first of all, let's look at the balanced equation then. So it says think about the reaction between magnesium and oxygen to form magnesium oxide. Now what we've got to remember is that equations are like chemical sentences, and I've just done the chemical sentence there as a word equation. So the plus sign instead of the and to form is where the arrow would be. Now we want a balanced equation, which means we need symbols. So magnesium is a metal, forms a giant metallic lattice, and therefore we just write magnesium, just Mg as the symbol. All metals will only ever have a single element symbol as their symbol in a balanced equation. No 2s or 4s or anything else after the symbol. And then we're reacting it with oxygen. Now oxygen's symbol is O, but we've got to remember that oxygen goes around as a diatomic molecule. So it forms O2. And then it forms magnesium oxide as the product. Now it might be quite tempting to write MgO2 because we're adding Mg and O2 together. But that is not the correct formula. We need to think about ionic formulae. Okay, magnesium is in group 2, so it has 2 outer shell electrons, and oxygen is in group 6, so has 6 outer shell electrons. And we can see here that when they react together, magnesium gives both of its outer shell electrons to the oxygen, leaving magnesium with a full outer shell, now the shell below its original one, and oxygen has filled its shell because it had 6 and now it has 2 extras. So the formula for magnesium oxide is actually MgO, just like that. And to make this balanced, what we can see is that we've got 2 oxygens on the left hand side. To ensure both of those are used, we must form 2 magnesium oxide molecules, or formula units, and then that means that we must start with 2 magnesium atoms at the beginning. So that's our balanced equation for the reaction. Next question then, if we started with 0.1 grams of magnesium, how much magnesium oxide would we expect to form? So we've got here that we're starting with 0.1 grams of magnesium, and how much magnesium oxide are we going to be making? So the first thing that we're going to do is we're going to calculate the mass of the thing we know the mass, calculate the moles of the thing we know the mass of, and that is magnesium. So we're going to work out moles of magnesium by doing the starting mass in grams divided by the relative mass of the magnesium, which will be 0.1 grams divided by the relative mass of magnesium, which is 24 grams per mole. That's from the periodic table. And when we put that into a calculator, that comes out to be 0.00417 moles. Now that we know the moles of magnesium, we can use the ratio and look at the moles of magnesium oxide formed. So there's magnesium looking towards magnesium oxide. We ignore oxygen completely. And the ratio in the balanced equation is 2 to 2. Now, 2 to 2 is the same as 1 to 1. So if we've got 0.00417 moles of magnesium, we would expect to form 0.00417 moles of magnesium oxide as well, because it's a 1 to 1 reaction. So we can therefore work out our theoretical mass of magnesium oxide, which would be the moles of magnesium oxide times the relative mass. And the relative mass of magnesium oxide would be 24 for the oxygen plus 24 for the magnesium plus 16 for the oxygen. So that is a relative mass of 40 grams per mole. And we put that into our equation at the bottom there, 0.00417 times 40 would be a theoretical mass of 0.17 grams of magnesium oxide formed if we started from 0.1 grams of magnesium. So that is a reacting mass calculation. And what we've just done there is we've worked out a theoretical mass. Okay, this is saying if the reaction is perfect, how much magnesium oxide would be formed if we started with 0.1 grams of magnesium. What we're going to look at today is the fact that reactions are very much not perfect and things can go wrong. And if we were in school doing this in the classroom, then what we'd be doing is a practical for this. And that's what we're going to have a look at now. So magnesium ribbon looks a bit like that. That's how we buy it in. We tend to only give out tiny little bits of it because it can get a little bit expensive. It's also very, very reactive. And what you might remember doing is in year 7, one of the things that we do is we put the magnesium ribbon into a Bunsen burner and it burns with a very, very, very bright white light. And that reaction you can see there, that is magnesium reacting with oxygen. It needs quite a lot of energy to start it off, which is why we need the flame. But once it gets going, you can see it gives out quite a lot of energy in a very, very bright white light. Okay, now I'd like to point out this is an animation I found on the internet. Okay, if this was in my classroom, people would be wearing goggles and have their hair tied back, but we shall not worry about that now. It's not my problem. Now, what we'd see if we did this reaction is that magnesium oxide forms as a white solid. And you can see here in the bottom of this crucible that we've got this sort of coil of ribbon that has turned into white powder. And if we were to poke it, it would crumble away. It would be very white and powdery. Now, the experiment setup that we'd do to investigate this, okay, and we wouldn't just stick it in with tongs as they are in that picture at the beginning. We would use this setup just here, where we have a crucible, which is what you can see in this at the top right here. That's a porcelain crucible, and they come with a lid. And we would put it into a pipe clay triangle resting on a tripod over a Bunsen burner. And we can see here just a slightly more sort of scientific diagram of that, okay, just with the labels. Feel free to pause the video and get that diagram written down if you wish. Now, one thing I found that I thought was quite interesting when I was looking for these animations online was this animation you can see on screen here, which is using a filter that removes pretty much all of the light. So it's about 99.9% according to the website that I got this from, and also sped up. So this is holding a bit of magnesium ribbon into light, and it's just quite nice and sort of shows the magnesium oxide forming there. You can see it crumbling to a powder at the end. So I just thought that was a little bit of interest. Now, I do have a worksheet for this, which you can download, but if you don't have the worksheet printed out, then what you need to do is to pause the video just here and to copy out the table that's on the screen. This is the table that we'd be filling in for the practical. So as I said, if you haven't got it printed out, just pause the video and copy that down. Press play when you're ready. Now, to look at what we do for this practical, the first thing that we do is to put a crucible with its lid onto an electronic balance and to record the mass. And what it says on the instructions is find the mass of a clean, dry crucible and lid and record it in a table. Now, it's really important that it is clean and that it is dry. If it's not clean, then there may be impurities inside that could react with magnesium instead of oxygen. And if it's wet, then you're going to be measuring the mass of that moisture, that water, and when you heat that up, you're going to be heating and evaporating the water as well, and so you'll get a mass change due to water loss. So it is very, very important that you do have these clean, dry equipment when you're doing these kind of experiments. That's the kind of thing they can ask in an exam. Why is it important that the crucible is dry? It's as I said, to prevent water being evaporated and sort of false mass changes being recorded. So once we've got the empty crucible measured, and it is important that we do that step, we would then coil approximately 10 centimetres of magnesium ribbon so that the coil lies flat on the bottom of the crucible. Now we want maximum contact between the bottom of the crucible and the magnesium ribbon, just so that we've got sort of that increased surface area for the heat to contact the magnesium ribbon to heat it up and make sure that we get a decent sort of quick and even reaction. One thing that can happen with this are side reactions where we get magnesium hydroxide forming instead of magnesium oxide. And as I said, if we can control the reaction and make sure that it's evenly heating, then that does help us prevent side reactions and decomposition and things. So once we've got our magnesium ribbon in the crucible, we put that crucible back onto the balance, and it must be the same balance to avoid any issues with changing equipment in the middle. And we would record the new mass of the crucible and lid with the magnesium ribbon inside it and put that into the table. So we've now got two masses. Now the two masses that we've got here, the empty crucible and lid and then the crucible lid and magnesium, that difference between the two is just the magnesium ribbon. So that allows us to calculate the mass of the magnesium ribbon. It's a bit more accurate to do it this way than just putting the magnesium ribbon onto the balance at the beginning, for a few reasons. When you're measuring small amounts like this, it just makes it a little bit easier to measure it when you've got a larger number on the screen. And also what you want to avoid is if we only measure the magnesium ribbon at the beginning, not in the crucible, at the end you would have to scrape out your product. And we'll talk about why that's a bit difficult in a bit. So after we've got the magnesium ribbon, we then put it onto our heating equipment. And what we can see is we've got this pipe clay triangle. Pipes used to be made out of clay. It's just a tube with wire going through it. And it allows us to rest the crucible down over the flame so that it's on direct heat. We don't want a gauze to spread the heat out. We want direct heat from that Bunsen on the bottom of the crucible. Using tongs very carefully. And what we do is at times, at intervals, we would lift the crucible to allow air in. We need to allow oxygen to be getting to the magnesium ribbon. But you have to be very careful to do this because you don't want to lose magnesium oxide. It will give off smoke when you do this. And if you do that, then you lose some of your product, and that's not very good. So really what you can see on the animation here is just so you can see the magnesium ribbon glowing white. In reality, you'd barely want to crack the lid. You just want to make a tiny gap to allow some oxygen in. And then what we've got here is step 5, turn the Bunsen off when all of the magnesium ribbon has turned white. This is the magnesium oxide, and you no longer see the bright glowing white when you lift the lid. That shows us that the reaction has finished, and at that point we would carefully lift that crucible lid, etc., and place it onto a heatproof mat. We don't want it to cool down really slowly, we want it to cool down quickly, and if you leave it on the heating equipment then it's going to take longer. So carefully lift that off, put it on the heatproof mat and leave it to cool, normally about 15 minutes for it to be cool to the touch. You never ever put hot equipment onto a balance because they're very expensive and they can break. So I'm going to skip straight to step 7, which is when it's completely cooled, you find the mass of the crucible lid and magnesium oxide again on the same balance as before, and you enter that mass on the table. So here is the table, and if you've filled the masses in, we started off with an empty crucible and lid with a mass of 32.34 grams. Notice that I have put grams on the left hand side. We don't need to put the G on the right next to 32.34, but we do need to make sure that we put the unit of measurement in the table on the left. The mass of the crucible lid and magnesium ribbon before heating was 32.74 grams, and as we can see from the picture on the screen here, the mass of the crucible lid and magnesium oxide, which was after heating and cooling, is 32.88 grams. Now from this information we can work out both the mass of magnesium ribbon at the start and also the mass of magnesium oxide formed at the end. So see if you can work out how much magnesium ribbon did we start with in the crucible and how much magnesium oxide did we end up with. Pause the video and see if you can work those out. So let's see if you have got those right. First of all, the mass of magnesium ribbon used is going to be number 2 on our table here, which is the crucible lid and magnesium, and we're going to take away the empty crucible and lid, and that would leave us just with the magnesium ribbon. So 32.74 minus 32.34, and so the mass of magnesium used was 0.4 grams. The mass of magnesium oxide formed is going to be the third value here, which is the crucible lid and magnesium oxide afterwards, minus the first value, the empty crucible and lid. So it would be 32.88 minus 32.34, and so we should expect 0.54 grams of magnesium, well, not expect, sorry, that is how much magnesium oxide formed, 0.54 grams. Now, as I said, what we're going to look at is whether or not that reaction was any good. Was 0.54 grams how much magnesium oxide we should have made? That would be 100% yield, a perfect reaction. Well, I'm going to tell you it's not. There's always going to be reasons why reactions are not perfect. And so a percentage yield calculation allows us to see that. So what we're going to do is we're going to calculate the theoretical yield of magnesium oxide. And this is how much magnesium oxide should have been made from the starting mass of magnesium, 0.4 grams. So this is exactly the same as the starter question. It's a reacting mass calculation. How much magnesium oxide should be made if we burn 0.4 grams of magnesium in oxygen? Reacting mass calculation. So pause the video and see if you can calculate the theoretical yield of magnesium oxide in grams. Press play when you're ready to carry on. As I said at the beginning, this is exactly the same as that starter question I put at the start. Instead of 0.1 grams, it is 0.4 grams. So we followed the exact same steps, and I've done a copy paste here. The moles of magnesium is what we work out first because we know how much magnesium in grams we have. So we do the starting mass in grams and divide it by the MR, which is 24 for magnesium. So we do 0.4 grams divided by 24 grams per mole. And so we started with 0.0167 moles of magnesium. Again, we now look at the mole ratio from the balanced equation, which if you remember from earlier on, and I'll just put it on the screen there, is a 2-to-2 reaction between magnesium and magnesium oxide. 2-to-2 is 1-to-1. So if we started off with 0.0167 moles of magnesium, we should end up with 0.0167 moles of magnesium oxide. And now we have the moles of magnesium oxide, and we can work out the relative mass, which as we said earlier is 24 plus 16, so is 40 grams per mole. We can therefore work out the mass of magnesium that we should expect to form. So the theoretical mass of magnesium oxide is moles times relative mass, 0.0167 moles times 40 grams per mole. We should have formed 0.67 grams of magnesium oxide. So that would be 100% yield. And yield just is how much is made. So 0.4 grams of magnesium should form 0.67 grams of magnesium oxide. But what you should notice is that the amount of magnesium oxide that was made in the pictorial experiment we did was 0.54 grams, and that is less than the theoretical mass that we just calculated should have been made from 0.4 grams of magnesium. We calculated that it should have been 0.67. So we've made less than we should, okay? The reaction wasn't perfect. Now we can calculate a percentage yield, and it's just a numerical way of saying how good the reaction is, similar to atom economy, but we're actually looking at masses here. So percentage yield is the actual mass that was formed in a reaction divided by the theoretical mass that should have been made, and that's all times by 100 because it's a percent. So if the theoretical mass was 0.67 grams, according to the mole calculation, but only 0.54 grams was made in the experiment, the percentage yield for this would be 0.54 divided by 0.67, so what was made over what should have been made, times by 100. And if you put that into your calculator, you'll find that it is 80.6%. So we've got nearly 20% there of our starting material that has not ended up as our final product. Now, 80% is not bad, okay? A lot of reactions are far, far lower than that. And if you were running a factory or you were making products for as a job, as like a process that you were doing, you would factor in your yield and you would know your yield for your process. And you have to factor that into your costs when you're selling products, and also consider how you could possibly improve that. Is there a reason why you've got 80% yield instead of 90% yield? 100% yield is extremely rare. And when I was at university, if you even got close to 100% yield in a practical, when we were doing laboratories, you generally got a rapping on the knuckles by your professor for having damp product. And, you know, that's not a good thing. So you're always expecting a very low percentage yield. And actually at university, if we were getting about 60% yield, that was particularly good. A lot of the time it was much less than that. So why do we not get perfect reactions? What can be the cause of this? Have a think. Well, what we've got to think about, we've said this already, even though no atoms are gained or lost in a chemical reaction because of conservation of mass, which is a law, it's not always possible to obtain the calculated amount of a product, and there are three main reasons. First of all, the reaction may not have gone to completion. Now, in this magnesium oxide one, that's fairly common, that you think the reaction has finished, but actually you've not quite heated it enough. It's not gone long enough. It could be that it's not full, the magnesium ribbon wasn't fully touching the bottom of that, the bottom of the crucible, and so a bit of the magnesium ribbon didn't get hot enough. If you're doing a decomposition reaction, it might be that it did not get to the right temperature. And sometimes people just get a bit nervous and they stop a reaction before it should. So that's a main reason why reactions are not 100% yield. Now, the other reason it might not go to completion is if the reaction is reversible. Now, many reactions are reversible, as we've looked at in kinetics. So the reaction can go forwards and backwards at the same time, and you're never going to get 100% yield if you've got a backwards reaction happening at the same time as a forwards reaction. So that's a very, very important reason. Second reason is that some of the reactants may have reacted in ways that were different from the reaction you expected. And I mentioned this earlier, that this reaction that we're looking at with the magnesium oxide quite often produces magnesium hydroxide instead. And so what we've got here are side reactions. And that's another very, very important reason for why we don't get 100% yield. The final main reason is that you might get a loss of product. And I mentioned this earlier. It's really important that we put that magnesium ribbon in the crucible and weigh the crucible lid and magnesium together at the end, together at the beginning. If we don't do that and we just weigh the magnesium ribbon on its own, at the end we have to scrape out all of that powder from the crucible. You're never going to get all of that powder out. You're going to be leaving some of it stuck on the inside of the crucible. So a lot of times you're going to get this transference when you're doing chemical reactions. So it could be that you've filtered, there'll be product left on the filter paper. It could be that product was lost when you lifted the lid. So there's all sorts of reasons why you may lose product. Good technique can reduce some of that, i.e. not lifting the lid too much. But if you're ever transferring between equipment, you are always going to get loss of product. So to finish off, we're going to have a look at an example exam question for this. So it says sulfur dioxide reacts with oxygen to make sulfur trioxide. The balanced equation 2SO2 plus O2 forming 2SO3. A. Calculate the maximum theoretical mass of sulfur trioxide that can be made by reacting 96 grams of sulfur dioxide with an excess of oxygen. And part B. In the reaction, only 90 grams of sulfur trioxide was made. Calculate the percentage yield. So I'd like you to pause the video, have a go at this question, press play, and I will go through the answers. Answer time then. So the first question is asking us to calculate the maximum theoretical mass of sulfur trioxide that can be made by reacting 96 grams of sulfur dioxide with an excess of oxygen. Now, first of all, if we have an excess of oxygen, we can just ignore that. We don't care. There's too much oxygen. We're not bothered by it. We are looking at what is known as the limiting reagent, and that is the thing that is not in excess. So we have 96 grams of sulfur dioxide, and they're asking how much sulfur trioxide can we make. So the first thing I'm going to do is I'm going to calculate the moles of the substance I know the mass of, which in this case is SO2, and that is going to be mass of SO2 divided by MR of SO2. The mass is 96 grams. Now the relative mass is 32 plus 16 plus 16, which if you put into a calculator or do this in your head is 64. I do recommend always using a calculator even for simple things like that, because in the heat of the moment in an exam it's very easy to make errors. So anyway, 96 over 64, that is 1.5 moles of sulfur dioxide. So looking at the equation, SO2 to SO3 is another nice 2 to 2 or 1 to 1 reaction. So if we start off with 1.5 moles of sulfur dioxide, we should also make 1.5 moles of sulfur trioxide. The question asks us to work out the mass of SO3. So we can therefore use the moles that we've just worked out of SO3 times by the MR of SO3 to work this out. MR of sulfur trioxide is 32 plus 3 lots of 16, so that actually is an MR of 80. So 1.5 times 80 and that comes out to be 120 grams is the mass that we would expect, the theoretical mass for part A. Should have put that just there. Now part B says in the reaction only 90 grams of sulfur trioxide was made. Calculate the percentage yield. So the percentage yield will be the mass we actually made, which is 90, divided by the theoretical mass, which is 120, times by 100 because it's a percent. And if you pop that in your calculator, it comes out to be 75% yield. If you need any help with that, let me know. Otherwise, have a go at the questions that I've set and get in touch if you need any help.